The second mode of heat transfer we are going to briefly examine is convection. Now there's an easy way to distinguish between conduction and convection. Recall that in conduction, the material being heated or cooled does not move, whereas in case of convection, the material actually moves. So convection occurs in fluids. I use the word fluid to denote both liquids and gases. The mathematical expression that allows us to calculate the rate of heat transfer in convection is called Newton's law of cooling. Newton developed this expression in the following manner: that if we have a heated metal plate which is in contact with air, and let's say the plate surface temperature is Tp and it is surrounded by air at a temperature of T infinity, and the area of that metal plate, the surface area, is A, then the rate of heat transfer Q from that metal plate, from the surface of the plate into the surrounding air, will be Q proportional to area times the temperature gradient. Now the temperature gradient in here is Tp minus T infinity. And if we remove this proportionality symbol, we can write Q equals, and we will need to introduce a constant which we call H, times then area times Tp minus T infinity. So this is a rather simple equation that allows us to determine rate of heat transfer from this metal plate into air if there is a temperature gradient between the plate surface and the air. Now H, the constant that we introduced, is called the convective heat transfer coefficient, and the units of this convective heat transfer coefficient are watts divided by square meter divided by degree C. So if we write that equation in terms of units, then the units for H are watts per square meter degree C times area is in square meters and the temperature gradient is in degree C. So degree C's cancel out, square meters cancel out, and we are left with watts, which is of course the unit for rate of heat transfer. So from this equation that describes convective heat transfer coefficient, if you increase area, you will increase the rate of heat transfer. Now next time you see a motorbike, look at its engine. Notice that there are small fins attached to the engine. Why? Because those fins increase the area for heat transfer, and it will keep the engine from getting excessively hot when it's driven and air blows past the engine surface. Also, from this equation, we note that the temperature gradient will directly influence rate of heat transfer. If the gradient is increased, then the rate of heat transfer will increase. If you lower the air temperature, then the gradient will increase. Tp minus T infinity will increase if T infinity is decreased. And so as a result, the rate of heat transfer will increase. Remember that I mentioned earlier that in convection, there is movement of the heating or cooling medium, which is in our case a fluid. Well, we can have two situations. In the first case, the movement is just because the fluid was heated, its density decreased, as you know from physics. This will cause buoyancy, and that fluid will essentially rise. Now this is called natural convection. In the second case, let's say that you use a fan or a blower to blow air on the heated plate. Now you are forcing movement of the fluid, and this is called forced convection. By using forced convection, we will get higher rates of heat transfer. This is reflected in the values for convective heat transfer coefficient. So let's briefly look at some of these values. For air, in case of free convection, that is when there is no artificial way of moving the air, the value for H is between 5 to 25 watts per square meter Celsius. On the other hand, if we have forced convection for air, then the value of H will increase from 10 to 200 watts per square meter Celsius. So as you see, there is a considerable increase in the value of H when we have some type of a fan or a blower. Now you know that because if you are holding a mug of coffee, for example, and if it's too hot and you want to cool it down, you blow air on it. So by causing the air to move, anytime you force air to move past that heated surface, you will increase the rate of heat transfer. And you are increasing the rate of heat transfer because you increase the value of H. Now, in case of water, for free convection, the value of H is from 20 to 100 watts per square meter Celsius. And for water, in case of forced convection, the value of H varies from 50 to 10,000 watts per square meter Celsius. In other words, in case of water, anytime you use for example, a pump to move that water on a heated surface, you will have a significantly higher rate of heat transfer. And in case of boiling water, the value of H is from 3,000 to 100,000 watts per square meter Celsius. Again, you get very high rates of heat transfer when you are boiling water. In case of steam, the value of H is from 5,000 to 100,000 watts per square meter Celsius. So that means that anytime we have forced convection, both in case of air and water, we have high rates of heat transfer, and we can get significantly high rates if we use boiling water or steam. This principle is used often in designing and operating food processing equipment. For example, if you wanted to freeze something, if you just place that product that you're freezing in an environment where there is no movement of air, the freezing time will be much longer. On the other hand, if you use an air blast freezer where you have some type of fan or blowers blowing air past that product that's being frozen, you can accomplish freezing in a much more rapid manner. So this is a brief overview of convection. Note that the equation is rather simple, Newton's law of cooling. One of the important coefficients here is this convective heat transfer coefficient that tells us how much heat is transferring from a certain area if there is a certain temperature gradient. Again, we will study this more in some of the other modules.